Thank you. Welcome, everybody. Thank you for making it. This is a special seminar. I scheduled this seminar after I've seen a paper, Steve give a paper at a conference, and I was so excited about what he was doing because there was such a large overlap with a lot of the work that we're doing here, particularly in the LAS context. That I said, you have to come, and you have to come right away. And so it's a pleasure to have him here. Dr. Steve Smith actually graduated from University of British Columbia in Vancouver in 1986, right?
That's right.
And then he joined ARM, which is kind of Lincoln Labs to University of Michigan.
Yep.
From 86 to 88, and then joined MIT Lincoln Labs, where he was doing adaptive signal processing and detection, decision, and tracking. And then, and also, he got his PhD in applied mathematics from Harvard University. He's received several awards, one of them being a SIAM Outstanding Paper Award in 2001. And he's been editorial board of the IEEE Signal Processing Society. And it's a pleasure to have you here.
And a pleasure to be here. Thank you very much, Hamid. Thank you for inviting me. Okay, so we're good on the audio? Awesome. Okay. Okay, so I'm going to talk about network detection today. And so this is going to be a problem where we're actually trying to, it's a small signal problem. We're trying to find small networks that live in a background of larger networks. And so the motivation for this problem, and you gave me this pointer, right? And, okay, so the motivation for this problem is that it exists in many diverse application areas. There's figuring out if you have a whole bunch of different connections that you can measure through a variety of sensors, wide area motion imagery, text. You can integrate a network in communication networks. By their very nature, are networked together. And as we know from the news, there's security aspects sort of this, and finding a network of interest within computer networks is an important problem. And this also arises in text analytics and even in biological networks here. And there's a lot of very recent work in figuring out protein interaction maps for various organisms. This one was published recently, and then the subnetwork is figuring out basically what the protein in DNA does. And so I'm going to motivate this problem actually with a clip from the film Battle of Algiers, which I think shows the problem of network detection very nicely, and is the only example of graph theory I'm aware of appearing in film. And so there's an audio clip. Will it come through? Hold on. Click to play. Okay. Thank you, Microsoft. I'm going to get it from here. Pardon me. Okay.
Comment les reconnaître? Le contrôle des papiers dans ce cas est ridicule. S'il y en a un qui les a en règle, c'est précisément le terroriste. Notez bien l'intuition de l'opérateur. Il a deviné que dans cette caisse, il y avait quelque chose d'important. Et il nous en montre tous les détails. Et dire que dans le double fond, il y avait peut-être la bombe, cachée. Mais nous ne le saurons jamais. Ça va comme ça, Martin. Nous devons recommencer à zéro. Les seuls renseignements que nous ayons concernent la structure de l'organisation. Commençons donc par celle-ci. C'est une organisation à pyramide composée d'une série de sections. Les sections, à leur tour, sont formées d'une série de triangles. Au sommet de la pyramide est l'état-major. Le responsable militaire de l'état-major trouve l'homme qu'il juge apte et le nomme chef d'une section, numéro 1. Le numéro 1, à son tour, en trouve deux autres, numéro 2 et numéro 3. Ainsi se forme le premier triangle. À présent, le numéro 2 et le numéro 3 trouvent deux hommes chacun. Numéro 4, 5, 6 et 7. La raison de toute cette géométrie est que chaque militant ne connaît de l'organisation entière que 3 membres maximum. Son responsable qui le choisit et ses 2 subordonnés qu'il a lui-même choisis. Les contacts se font uniquement par écrit. Voilà pourquoi nous ne connaissons pas nos adversaires. Parce qu'en réalité, ils ne se connaissent pas entre eux. Les connaître signifie les éliminer. Il en résulte que l'aspect purement militaire du problème n'est que secondaire. Celui qui est mis en évidence, c'est l'aspect policier. Je sais bien que ce mot ne vous plaît pas. Mais c'est le seul qui indique exactement quel type de travail nous devons entreprendre. Nous devons procéder aux recherches nécessaires afin de reconstituer toute la pyramide pour arriver à l'état-major. La base de ce travail est le renseignement.
So I really like that clip because it shows basically all the kinds of features that we're going to talk about. In network detection, especially in the kind I'm talking about, you're looking for covert networks that are going to take active measures to try to remain covert. It's not going to be an easy type thing. And then the way you do, the way you address this problem is to basically follow the leads and see where they go. And so let me pop back into this player here. Okay, so you need 2 things then for covert network detection. You're going to need algorithms that can use the network observations you've got, and you're going to assess what you're doing. You're going to need some methods for quantifying what kind of detection performance you're getting. And this has to be done in the context of the properties we just talked about. You know, tautologically, covert networks are covert, and they're going to use security to avoid detection. And also, and this is going to be an issue, is that they are connected to large active background networks. You know, so most of what's going on you don't care about. And so some themes that you'll see here is that both the issues of observability is, you know, if there's something there, but have I actually observed it? Is there the data to support it? And detectability are going to be important. And although I'm not emphasizing this, I think the reason that I'm glad I came is because there's a lot of other mathematical themes that I'll hit on too. So there's going to be things like graph Laplacians and harmonics and all this stuff. We can talk about some of the mathy stuff. I've actually prepared these view graphs for a higher level audience, so I'm glad to be here to talk with you guys, to dig in some of the details. Okay, so now I want to talk about detection algorithms, and this obviously is going to be the body. And I'll talk about the network detection problem more specifically first. So this is the network detection problem is a specific case of the graph partitioning problem, and I've shown an example here. You've got a big graph, and you want to divide it into pieces that are relevant to you, and the pieces might be country, or they might be different consumer groups, or they could be the network you're trying to detect. And so this is really a binary graph partitioning problem. So you've got a big network, and you're basically trying to decide who's in and who's out. And how are you going to do that? And so there's a whole suite of algorithms for network detection. And so I've put together this taxonomy to describe what they are, using both the application area and the general mathematical approach used to solve the problem. And so this is a binary hypothesis problem. This really, you know, if you've got n things in your graph, if it's of order n, then you've got 2 to the n decisions to make. And so this is an NP-hard problem. And of course, you don't want to address NP-hard problems, so you do what everybody else does. You try to relax that problem down. And so different relaxation methods, and it depends really on the kind of application area you are, which one of these you have to use. There's general optimization methods which use SDPs or linear programming. You can also do things like deal with the topology of the network. So you have some topological thing you care about, like connectivity or whatnot. And these problems typically reduce down to computing eigenvalues and eigenvectors. And so what I'm going to talk about here and compare them to some of these methods is optimizing the detection probability. So our optimality criterion is going to be, hey, you're trying to detect this thing, optimize the probability of detection subject to some fixed false alarm rate. And this will reduce down to a Laplacian system. And so, and then I won't talk about all the algorithms, but obviously this is Laplacian systems. You're doing matrix inverse, so there's fast, efficient algorithms for that. And at least, you know, if you're an so compared to eigensolver land, where you can get, depending on the connectivity of the graph, you can go n or n squared log n, or even up to n cubed, depending on sparsity. There's some computational advantages, and there's computational advantages to STPs as well. But you know, it's all better than solving the NP-hard direct approach. So now I'm going to talk about two different descriptions of this problem. First, a random walk description, and then a probabilistic description. And the efficiency thing is they'll end up being exactly the same. And by the way, I prefer questions as I go. So if people have, I'll take questions at the end too. So if people want to pipe up, that's fine with me. So let's talk about this random walk model. Here you've got a graph, and I'm going to talk about the simplest possible model where I've got two things in my graph. I've got this thing I observe, and I want to see what the relevance is of the thing I observe out in this vertex. Now here there's this thing I observe, and there's only one connection between the two. So if I'm calling, if this is threatening here, and I want to compute the probability of threat there, there's only one way I could go from here to here. So the probability of threat over here is the probability of threat at my observation. Given the probability of threat at my observation is equal to just what's the probability that I had that observation to begin with, multiplied by the observation that it could move between the two. So that's pretty simple. And if there's still one path between my observation and my vertex, but you've got multiple hops, this hop, this hop, this hop, possibly with different kinds of pieces of information, then it's still simple. You just string these things together and you multiply what the probability of threat is moving along each one of these legs. So that's simple. But in the real world, we don't just have one possible path. We have a whole bunch of possible paths between where we observe things and where we want to compute the probability. And we don't know which path the threat could have taken. And so the approach is to compute all of them. For each path along here, you compute this probability, and then since no one is necessarily any more special than any other, you just compute an average over all possible paths on the graph, which is this infinite sum. And this gives you, if you do this infinite sum and take the limit, that basically gives you that the probability that there's a threat at the vertex you care about is equal to the probability that there's a threat at your observation, multiplied by the probability that you've got this path from your vertex to your observation. And so this is conceptually very simple. You can build it up from the simple one path to the full graph. So conceptually very simple, but computationally terrible, because you don't want to be computing an infinite number, or a large number, or Monte Carlo number of random walks on graphs. So I'm going to talk about a computationally attractive approach that turns out to be equivalent to this random walk description. Any questions? Yeah.
Wildly different lengths.
So if you tell me
by, say, the length or the probability that you get a given path?
Sure. So if you tell me that if you put a prior on some paths are more reasonable than others, then certainly you could incorporate that prior. But then, modulo a prior like that, so you're taking a weighted average rather than an average. It's the same logic. You still have to.
But you're not weighting here in this formulation.
So implicitly, there is actually there's a model that I'm going to, I'll defer you to a paper at this point. There is a model for how one might compute these probabilities. And so these probabilities might be, hey, these two things happened at the same place in the same time. I'm going to give that a lot more weight to something that may have happened at the same place, but if somebody comes into this lecture hall, 3 days later, probably not, related. So there is a weighting like that in there. And like I say, this is going to appear in the IEEE transactions on signal processing. So, and there's a whole way in which you would choose, a reasonable person would choose that. So I don't want to gloss that over, but it's still, however you choose that, you still have to, in this model, you still have to compute all these paths, and whatever weighting you think is an appropriate one, add them all up, weighted appropriately. Okay. So now let's talk about, that was a random walk description. Let's talk about a probabilistic description. So let's start out. I'm at V here. I want to compute that there's some probability of threat at V. It's a graph. It's a network. So the only way threat can get to V is through its neighbors. So the probability that there's a threat here is equal to the probability that it was at its neighbors, which in this illustration is either 2 or 4, and that threat went from 2 to V. And so you just apply the additive law for probability here, and with independence, and you get this probability of threat at V. And so this is Bayesian, so it's really not, it's probability that the threat at V given some observation of threat. And I'm using threat here as really a motivating example. It could really be some, any characteristic or property that is relevant to you that you want to diffuse along this graph. Let's call it threat for the sake of argument. It's really the probability of threat given an observation here. So fine, you just condition everything based on that observation. And now, for all other vertices in the graph, it's the exact same logic. So the probability of threat at 2 is its neighbors, which are 1, V, and the observation. And at 4, 1 is 1 and V. And you just go on, so on and so forth on down the line. And so what I'm doing here is I'm building up. You start with a graph, give an observation, you apply some Bayes rule. And so on isn't a very good algorithm. But if you look at these equations, this is obviously a linear system for all the threat probabilities, which, as we'll see, involves the graph Laplacian directly. So let's solve that system. And I'll also note here that, I think it's intuitive, but we describe this exactly in our paper, that these are equivalent approaches. These are both, whether you piece your random walk together sort of all at once and talk about paths, or you talk about each link separately and then all averaged together. They're different ways of describing the same fundamental description of the problem. So if you write down this linear system for what the probabilities are, you have your observation probability. Well, that's fixed. And then you got all the stuff you don't know, and that's what you need to compute. And so this is a straightforward boundary value problem, where this matrix here, you multiply this matrix times your vector of probabilities is equal to these probabilities. This matrix is the adjacency matrix for the graph, which is, ij is there. If ij is in here, then an edge exists between vertex I and vertex j, and you solve that. And one way of solving that is you can express things in terms of this graph Laplacian, which is basically the identity minus this adjacency matrix. And what you're trying to solve is the Laplacian times some unknown vector equals 0. That's a harmonic, so what you're looking for is a harmonic function. And this is a boundary value problem because what I've shown here is one of these observations is fixed. It's the prior, it's the Bayesian prior, and you can have one or you can have multiple, it doesn't care. And so you have a fixed Bayesian prior, and then you just solve the system. And so, and this system here is just an inverse of your Laplacian. And this is, because it's a boundary value problem, this is directly analogous to thermodynamic diffusion, basically any harmonic system. And so, and it also shares some of the nice properties, and we're going to, understanding some of these properties is going to be important. For example, the mean value theorem, that the value in the middle for solutions like this is equal to a average along a path in this particular example, or in our case, just the vertices. The average in the middle is equal to some average of your neighbors. And so that gives you this algorithm, which is, I mean, I'll talk about why space-time in a second, but that gets into this, not just this place, but this place and this time. But it's really, abstractly a graph, whether it's a graph or a space-time graph. So you have this graph of connections you've got some observations, you apply Bayes' rules, and you've got a detector. And so you compute the solution, these threat probabilities, and then you threshold. And if you get a new observation in, you can just apply the matrix inversion lemma and do this Bayesian update on your answer, or you can recompute. And so when you set this threshold, this gives you a subgraph, and anything above a particular threshold you declare to be in. And so this gives you a network detection algorithm. And so why space-time? I'll say one of our examples here is because we've got links not just between our entities occur in both space and time. And so this is this model I was talking about. And so for you have different kinds of observations, then you would have a different kind of model. But here you've got an observed threat. So things happening at the same place in the same time, threat likes to propagate, according to this model, more than if they are separated in space or separated in time. So if you've got observed threat here, this will propagate through your space-time graph along this length a lot better than it will propagate when you have separation in space and time. And so now I'll talk about optimality, and I'll just mention that so if you express this network detection problem as a detection problem and say, okay, I want to turn the crank and come up with the optimum detection strategy that's going to maximize my probability of detection given a fixed false alarm. You do that, and just like standard Neiman-Pearson detection theory, what happens is you get this likelihood ratio that pops out. So this is all classical, except we're applying it in this network detection concept. And so the likelihood ratio is the probability of your data given that your vertex is in the foreground as a ratio of the probability of your data given that it's in the background. If this is greater than some threshold, then you say it's in the foreground. Otherwise, it's in the background. And so your foreground is the things most highly correlated with your threat observation by definition, or it's the thing you're trying to detect. And so you basically have two hypotheses. It's either it's in the foreground or it's not in the foreground. Just like classical. And again, I'll defer to the paper for details. And so this process, you can show that this process, this likelihood ratio test, computing that is exactly equal to this Bayesian threat propagation scheme I just described, where you're taking threat and you're propagating it through your network and computing threat probabilities that way. So if you can compute threat that way, you are computing the Neiman-Pearson solution to the detection problem And therefore, you've got a optimum network detector if threat propagates according to this random walk model, number one, that, well, that's pretty much it. If threat propagates according to that model, it's optimum. So yes. So this is a random variable representing your observation. And so this could be fixed, like, hey, that's threatening, or I know for sure, or I'm not. So this is your observational data at a specific vertex. Yes. So you've got the data that you use to build what your graph is, and then at a vertex, possibly at a specific time, you've got some observation, and that diffuses out through your graph. And then from that, you want to decide, which of your vertices are most highly correlated with your network. And it turns out when you do this in the way I described, you can show that it's an optimal detection test. And that's nice because you've got a nice algorithm to do it, and that'll give you some that gives you some confidence that if your assumptions are right, that's how threat diffuses, that you've got a good algorithm to do it. And also it gives you a bound on what kind of performance you can expect to see in this kind of problem. And so now I want to spend a little bit of time comparing this approach to other network detection approaches that are out there that are fall under the guise of community detection. So with community detection methods, what they try to do is they try to optimize this topological connectivity. And so if you divide the world into how much foreground activity is there and how much background activity, if what these methods try to do is detect activity, and then if there's a lot of activity, then you assume threat. And what I've just described is you don't have any assumptions on foreground or background activity. What you're trying to do is optimize a completely different metric, that is the probability of detection. And so now this gets into some of the math behind some of these methods. This approach goes way back to some of the earliest algorithms for network detection. There's, for those of you familiar with Fiedler values and Fiedler vectors, this is great stuff. So what Fiedler did was he showed that if you compute not the first but the second eigenvector, the Laplacian, and not the first eigenvector, because as we all know from this mean value property of Laplacians, that solution is going to be constant. Basically, what function has the value of it's the average of its neighbors, the constant one, obviously. And so if I'm computing a constant function, that's not a very good discriminator about who's in or who's out. And so one thing all of these methods share is how you get around that problem of the Laplacian. Obviously, fundamentally, the Laplacian is very important in describing the problem. But if you look at at its most basic properties, they don't help you with the detection problem. And so what Fiedler did, he came up with like the first relaxation approach, essentially. And he said, well, we're not going to look at the first eigenvector. We're going to take a look at the second eigenvector. If you take that eigenvector and threshold that, and this is a cool proof, he showed that all the vertices associated with the biggest values of that components of that eigenvector, that gives you a connected graph. And so that's a network detection method. And so that's pretty interesting. And it has to do with various things you're optimizing, and you can dig into that. And so the issue with that is it's very, very interesting mathematically. It's quite innovative, but it doesn't give you a very good network detection algorithm. And so even though, if I have time, I'll talk about some of the nice properties of Laplacians why people still care about Fiedler values and Fiedler vectors. And so what Mark Newman did in the 90s is he came along and he suggested an alternate approach which would, let's see. What Mark Newman did is he came along and approached an alternate approach where rather than optimizing the Fiedler criterion, which, by the way, is basically how many edges you have to cut to pull out your network. And that's another insight, is that how do you optimize that? Well, you either cut 0 of them, and it gives you the whole thing, or you cut all of them. And so what Fiedler did is he developed a way of maximizing what he called the modularity of a particular network. And this is, the way to think about this is he's trying to find a network which has the most activity within the subgraph relative to the background. And so there's a new matrix here, the modularity matrix, which is the adjacency matrix minus a rank 1 down date. And the solution is still an eigenvector solution, but now it's an eigenvector of this modularity matrix. And this gives very good partitioning performance with active backgrounds. And so this algorithm looks like you form your adjacency matrix, you compute eigenvectors, and you perform a selection on your eigenvectors, and then you do a thresholding in eigenvector space, and that gives you a subgraph. And so, and then here's another picture of showing the performance as where your foreground activity is the same as the background as you expect. You don't get discrimination between your foreground and your background with these types of methods, or where it's you have a very active background compared to the foreground, and here you get great separation and a good detection algorithm. And I'll talk about more topological issues in the next section. What am I doing here? Okay, so now I want to talk about performance results. And so this view graph describes how you do detection performance assessment and some of the challenges associated with that. And so what you'd really like is high accuracy, high fidelity results across a range of different types of graphs. And so really sort of the gold standard is a real data example where you know the foreground network you're looking for and its connection to the background network, so you can assess how well you're doing. And so the real data examples we have is basically, you can read 0 of these. If anybody knows of one, please come up after and let me know. But this is very challenging for all the reasons you can imagine. And so people fall back on various empirical results. And I would say a very exciting new development, I'd say quite amazingly so, is analytical results in this area. And so with empirical results, you can either run Monte Carlo or you can do one-off experiments for this and see how you do. And so these exist, and that's what people do. And so also what exists, and this is work by Raj Rao at the University of Michigan and in collaboration with Mark Newman, is to do closed-form analysis, detection analysis, using very simple models. And so where they've started is with detecting cliques embedded in Erdős-Renyi backgrounds, and where they're moving, and this is in collaboration with a project we have together on this problem, is to analyze more complex models that have community structure, block model structure, small world properties that you don't find in cliques or Erdős-Renyi models. And so I think it's pretty remarkable that you can think about closed form analysis in these graph analytic problems. And I've written down some of the citations here, and you can find a lot more on arXiv. And so I'll just show some results here that we have for our empirical data sets. This is a simulated data set of wide area motion imagery, and this takes place over a couple-day period. There's a handful of foreground entities that one cares about in the background of thousands of things you don't care about. And this shows the performance of, in this one particular instance, of this network detection algorithm. And because of the property stated before of optimality, I think this gives you a bound on the kind of performance. And so, by the way, for those of you not intimately familiar with ROC curves or receiver operating characteristic curves, what I'm plotting here is the probability of detection, in this case the percentage out of 31 foreground entities that you know to be true or that you've modeled to be true, versus the probability of false alarms, things that you don't care about. And where you'd like this to be is you'd like to have 100% probability of detection and no false alarms. And of course, you never ever get that. And so the further you are up on this curve, the better you are. And if you're doing no better than chance, you get a straight line here. And that's poor performance. And so this gives us a good bound on performance. And so we also have experiments with various data sets. And I'll, in the interest of time and answering questions, I'll skip over that. It's a very similar result. And now I want to talk a little bit about modeling this. Those were two single experiments that that you get. So, you know, empirical of the thing in the sense of I ran this simulated data set and I got this one particular result. Another way is you generate lots and lots and lots of graphs using a graphical model that you think is representative of what the real world is. And the simplest thing to do is you have an Erdős-Renyi model. And the way to think about this is if you have an Erdős-Renyi model, the cool thing that Erdős-Renyi introduced was their paper is important not just because they have this model. An Erdős-Renyi model is where the probability of connecting two entities in your graph is p, and it's the same between any two entities, and that gives you a graph. So that's a nice model, simple model. But also what they showed was that there is a phase transition, a sharp phase transition for p. If p is less than log n over n, where n is the order of the graph, then your graph is almost surely disconnected. And if it's greater than log n over n, then it's almost surely connected. So that's a really cool property. And so you can think of Erdős-Renyi as sort of the connectivity. It satisfies a connectivity constraint for you. And I'm going to talk more about phase transitions in the context of detection in a moment, since this theme continues into detection theory. Stochastic block models. So Erdős-Renyi doesn't know anything about communities. Block models do, and these basically get into they treat your graph that each entity can belong to a variety of communities, like each of you belong to a family, you're associated with NC State or whichever communities people belong to. And then Chung Lu, this gets into a kind of the degree distribution of the graph, and it has to do, you know, a common term is, you know, the Kevin Bacon 7 degrees of separation is that Erdős-Renyi doesn't have, is that all of us are what? Connected to 7 hops anywhere else on the planet. Erdős-Renyi doesn't have this, but networks especially involving people, seem to have this kind of property. So you want to have this property. So we have this model that is comprised of the 3 basic ingredients we want: connectivity, community interaction, and scale-free dynamics. And we use this to generate lots and lots and lots of graphs, and that allows us to do Monte Carlo and empirical results. So here's a result showing the probability of detection versus the probability of false alarms, or in this case, the number of false alarms for a random network. And this is the size of the network. And so now this quantifies how this task is getting more difficult as the order of the graph increases. Basically, as the order of the graph increases, there's essentially, more places to go and hide, so you'd expect your ROC performance to go down. And this gets into the topology, and getting back to that clip I showed from Battle of Algiers, is that if you use what is claimed to be an intuitively a difficult topology to detect, a tree network, this shows the performance and the impact of the performance if you have this topology. And it goes down, not surprisingly. And so where we're at now is we can compute these things empirically, but it sure would be very nice to push some of the analytic results to quantify some of this stuff parametrically. That would be a nice result. And so, and one can do, since we have if not parametric analytic insight into this problem, parametric control over our empirical simulation, we can do assessments like look at how many observations we get with varying accuracy on those observations, and then see how many more observations we need to make up for inaccuracy in any of our observations. Yes.
Is the problem just to detect if there is such a network in there, or to actually find out where that network is?
So the problem is to identify which vertices in your large network that you have belong to this foreground network.
So in that case, so how would you handle the case where you only identify part of the network? Is that do you consider that detected or not? So, well,
with the nature of rock curves is, I mean, you're going to have some false alarms, and so you can't, it's like any detection problem, is there something there or not? And you have something, you say, okay, it's there. And then what's your chance of getting it wrong, and what's your chance of missing it? So, type 1, type 2 errors, probability of detection versus probability of false alarm. So what I'm showing here is, I'm showing is you sweep a threshold, in this case over these probabilities, or if you're doing a community detection, you're sweeping it over the eigenvector. What I'm showing here is the probability of detection. Since these are simulations, I know what truth is. What percentage did I get right, and what percentage did I get wrong? And so at the end of this, you would say, I mean, basically, you have some operating point you care about, and then you would have to go have subsequent means of dealing with the question you're asking is like, how do I follow up and make sure that, I deal with my false alarms in an appropriate way, and the fact that I didn't get everything in an appropriate way. So, yes.
About generating the background graph using a model.
Yes.
Like RMAT or stochastic block.
That's right.
Do you then superimpose a randomly generated
That's right.
network, or do you sub-select from the original?
You can do either, but we superimpose so that you have a separate model. So, for example, I showed the tree structure. So here I'm superimposing. This is an Erdős-Renyi superimposed. But
so if those edges existed in the original model, do you duplicate them?
So, well, now, so there's a question essentially on multigraphs, and so we do have a way of dealing with multigraphs, but for these simulations, it's a big or.
Okay.
Okay, and so I think actually I'd like to talk more about the math here, but basically this gets into, we're talking about workflows and frameworks here, and so how do you deal with this large data problem? But for a math community, I'd actually like to take a couple moments and I won't read my summary here since you just heard me. I'd like to talk about some of the background and maybe leave off with some of the connections, since that's what we're here to discuss. So, I think, so the background for all this stuff is algebraic graph theory, and I think the appropriate way to think about just to say, for those of you who work in detection theory or know about detection and estimation, linear algebra is the foundation for that. For network detection in these problems, algebraic graph theory is, I think, clearly the foundation. And that's because of the existence of all these graph matrices, the adjacency matrix, the graph Laplacian, and harmonic solutions. And so there's some quick background here on this, and maybe I'll, and so let's see. Let's see, I think another thing I'd like to mention that came up in this for you, in our discussion before the talk, is there's very nice connections with this, with graph, basically all problems in the physical sciences are essentially graph problems because you got to solve, or you have to solve them, and so you discretize the problem somehow, and that gives you a discretization on the graph. And so these graph Laplacians are really these Laplacians that you encounter in Riemannian theory, and have all these nice generalizations in Hodge theory and pop up. And so I think we can discuss this more after the talk. And so there's some very nice connections with what's going on in all the network detection stuff we talked about. And for those of you familiar with solving physical problems, like problems with Green's first identity, like finite element methods, the Laplacian shows up in all this stuff. And so, and just very quickly, here's some. I've provided a summary of some of the topological reasons why people care about these Fiedler methods. For example, the number of connected components is how many times the smallest eigenvalue of the Laplacian is repeated. If you have one component, then there's one of these things. If you have two, and this is easy to show. The connectivity is also coded with this so-called Fiedler value, and this is what I talked about before. If you threshold this eigenvector, then you're guaranteed to get this connected graph. And the eigenvalue associated with this has all these nice bounding properties that involves the order of the graph and the graph diameter, and so as well as the graph volume. So you have all these inequalities. So if you compute this so-called Fiedler vector, the eigenvector, or excuse me, the eigenvalue associated with either the graph Laplacian or the normalized graph Laplacian, then you have some sense in what the smallest diameter volume is on the graph. And so that's a nice thing to have. And so you can see, basically you can see that here. Small Fiedler vectors are relatively small for tree-like or very highly disconnected graphs compared with more connected graphs, Erdős-Rényi or RMAT. And so, and I'll leave it at that and take questions.
Any question?
Yes.
Yes, Blair.
So if he has a question, he can go first. I've already asked him.
Okay.
I actually have two questions, and the first one is more of a clarification than a question from my own education.
Sure.
I mean, we in our research we do deal with a lot of graph theory and algebraic graph theory actually.
Yeah.
But the context actually is very, very different.
Yeah.
So what I wanted to clarify is, the initial graphical models that you were stating.
Yep.
So it looks like in the context of network inferencing, graphs come in a very different way than usual engineering applications. Like for example, so the way we deal with graphs is that there is a actual physical network or an engineering network, for example, which actually exists over a topology.
Yeah.
And then we do analysis on that topology.
Right.
But from the models that you stated, it looks like there is some discrete event system, and the analyst himself creates a probability distribution model to describe the discrete system, and then does analysis on top of that.
So,
So the nodes, for example, in your case, are probability distributions or
right.
variables, and then the edges are
right.
variables are correlated in any way or something like that. And the person who is analyzing this whole thing is creating that graph himself. It's not given to him.
So there's a couple things. You find this in the modern, in lots of applications. So sometimes you have all the data, you have all the, and so you would say, like, if you're Google, it's like, here's the graph we have. It's like, here we go, and you can do anything you want. But some applications, it's very, very expensive to generate the graph. And if it's very, very expensive and you don't care about most of it, then then you've got a prioritization issue about what data am I going to collect. So I think you're asking a very perceptive question, because part of this is a sampling. This gets into sampling issues, and you can actually use these methods to point to where you should sample your graph next. Basically, you said this was important. Where should I direct my finite resources to build out my graph further? So that would be one response to that question. And then I think the response to your first question is how do you basically have a model on these vertices, and then how does the analyst interact with that? And so I'll defer to our paper, which is on archive right now, but the answer is pretty simple. It's basically for the kind of connection you're making.
My question actually wasn't that.
Sorry, pardon me.
My question was that how does the analyst even construct this graph when it doesn't follow from an actual physical system? This looks more like a cognitive graph, basically, where he has to keep track of in his own brain that, okay, so does this happen if this happens, or if this happens, then if this happens, and there's a lot of statements behind this.
Oh, no, this is specific. This is a specific physical graph. Like, you have, basically, there's something happened here, and then you have a track from this site to this site. And, things left here and arrived here at this time. Or it could be a computer network where you have these packets leaving from this computer and going to this computer. So, yeah, absolutely.
My second question is that it's also maybe a little benign, but I'm a little rusty on these kinds of network things. So you said that you apply Bayesian on these once you have the Covert models.
That's right.
And then, all throughout your derivations, you're using actual equality signs and not proportionality signs, right? So, if I understand Bayesian properly, so in order to calculate the posterior, you need this normalization factor, and typically, the way we calculate the normalization is using Metropolis and Hastings algorithm.
Right.
How do I apply Metropolis and Hastings on a 1,000-node graph like that? That's going to be computationally exploding, right?
So no, actually no. These are actually normalizations are in here, right? So this equation, this is an exact equation. So you don't have to. So you don't have to do Metropolis Hastings. You don't have to do. These are the algorithm. That's an exact. These probabilities just work out. You can show that. So if you basically, for example, to compute this probability, one way to compute it would just to be launch a zillion Monte Carlo runs and see which fraction gets there.
Right, but you made it.
So I guess is one way of answering your question about.
In your talk, that was exactly my point. That in your talk, you actually said that Monte Carlo is probably not a good idea because.
So if you didn't have this equivalent probabilistic approach, then you would have to contemplate doing something like that. But thankfully, thanks to the properties of harmonic systems, you have this very nice algorithm that is well studied. It applies directly in this case. And so what you're paying for that niceness is you're assuming that you've got this Markov chain, that basically things diffuse around your graph like this Markov chain. And so in the real world, it won't quite be like that, but it will be almost be like that. And so I think that's why this is a nice method.
Glenn?
I was going to ask, you had a mixed membership block model mixed with Erdős-Rényi, mixed with Chunlu.
Yes.
To me, that sounds very reminiscent of this work out of Sandia on Beater, which is a block 2-level Erdős-Rényi. I think they're just mixing Erdős-Rényi and Chunlu, but are you familiar with that?
I am not, but I'll get a citation from you after the talk, and I appreciate the comment. Thank you.
Any other questions? I do have a question. Is actually it has to do a little bit with what Aranya was asking about. Who gives us these probabilities? Is my
Oh, so which probability? These ones?
Yeah. But for instance, those conditional.
So this is your prior. This one's your prior.
No.
So this you got to compute.
Right.
The whole problem is to compute these. This is your prior, and then this is the problem we're solving. How you compute what this is, and the way you.
That's a transition, right?
Yeah, and so the way you compute that is this. And so you've got a Bayesian here. This is your known. Right. These are your unknowns. Right. Here's the linear system. You crank through that, and you get the solution to the standard boundary value problem. It's just a matrix inverse involving the Laplacian. It's just like any other boundary value problem that you ever solved. So you're computing these probabilities. And so these probabilities are the probabilities of threat given your prior. And then you threshold those probabilities, and those, I didn't talk about that. Again, referral to the paper, but basically you're guaranteed to have a connected subgraph detected out of that from this nice property of things at the center are an average of things around them.
And this prior, of course, you have it from some.
Oh, and so that's a good question. So if in the illustrative example, something blows up, that's threatening, and it might not be so clear. In which case, you'll have a model for. You would need a model for your prior about how do I have some observation here. How do I translate that into a probability? So there is an observational model implicit in what I'm talking about here for real applications. Or it could it could just be, hey, if this happens, the probability of threat is 1. You had a question?
As a follow-up to Dr. Craig's question, if you flip back to the Bayesian model graph, so here, when you're computing the conditional probability of, say, that if we're the probability of threat at V given node 4, that conditional probability.
Yes.
That is computed from the graph propagation, or that has to be known or estimated somehow?
That is computed through this method. So the probability at 4 is equal to the probability at V and 1. And the probability at 1 is equal to 2 and 3 and observation, and so on and so forth. And so that gives you this big linear system, and you solve a linear system with a matrix inverse that is the Laplacian.
Any other questions? Yes?
Hi, Professor. I have a question. Because I've noticed two things. First is that you assume all the events are attacked. And actually, how do you decide edges between them, the links between them? And the second one is that I noticed that when you were using the adjacency matrix, you assume that the graph is undirected. But actually, if we follow a time sequence or something.
That's right.
Yeah, it's
so
it could be directed. So does it matter?
No, great question. So the way you establish, first of all, the way you establish connections between things is, with the data that you have to construct your graph. So we talked about cyber as an example. So if you have, basically IP packets going from this computer to another computer, that would be, you would draw a link between those computers. And the IP packets would have, they'd be on a specific port, and they'd have these properties. So you could get down into what kind of link that was. But conceptually, it's like that. And maybe in that case, it happens so fast that you don't care so much about timestamps. Maybe you do. But in other problems where it's like tracks of vehicle tracks or things like that, then the timestamp does matter. And so you could have, and in that case, you don't have a symmetric adjacency matrix. And in fact, you do not need, and I'm just putting one up here for illustrative purposes, but that's a good way. You can have asymmetric, it doesn't have to be a simple graph.
Okay, but in that case, the graph Laplacian might be different.
And the Laplacian is different, but you're still, you still have, if it's strongly, so now you start invoking Perron Frobenius, and so if it's a strongly connected graph, or if the Laplacian is irreducible, then you can make statements about if you can solve your problem or not. So, but and again, this is all in the paper I'm plugging here, so it's on archive. But if you look in there, you'll see an extension to the Perron Frobenius theorem that allows non-irreducible matrix, and that talks about the conditions when you can solve this problem.
Thank you.
Okay, thank you.
Yes.
Yes.
Yeah, I have a question regarding how you will construct such a graph, because as long as I know, for many networks, it's not only related with the place, like temporal, and there's spatial and temporal correlations.
Yes.
And for one time, you have a graph constructed, and then, but when time evolves, and then this graph may change.
Right.
And then you will have another set of it.
Right.
But when you detect this system, I think it should be based on a observation over a certain number of months or even years.
Yeah.
So when you handle these kind of situation, when you consider these background and foreground stuff, are they related with that time series?
Yeah. So that's that gets to our description of this using a space. So I think it's fair to say that there's two ways of describing graphs with some dynamics. One is, you sort of have this graph, and these edges can, pop in and pop out. And so, and in the way I've described here is you actually have, you don't think of a spatial graph with time-dependent edges. You think of a space-time graph with relationships of this vertex at this time connected with other vertices in other times. And so, so using that description, which I think covers the case you're talking about, you can use these methods to solve the network detection problem, even if there's not a single track like the kind I've been describing.
So are you saying all this method actually is snapshot for the whole system? You have to take snapshot and do the analysis, and then do another snapshot and do another analysis, and then connect them together.
So this is not a snapshot. This is comprised of your graph over all vertices over all time. So there's no, it's like you've got a space dimension and a time dimension, and you're looking over that whole space-time volume that your space-time graph lives in, and following things around in space-time paths. So I go, like when I got here, I left Logan and I flew here, and that's one point, Logan is a different place now than when I left it this morning. And so I'm talking about vertices at a specific places, time and place to time and place. And so that's not a snapshot. That's a point in space-time to other points in space-time.
Yeah, I think you can do that, but then that means all the probability and everything is a function of time.
That's correct.
And then it will make the problem extremely hard to solve because you will soon running into dimension problems. Because you can solve it on at one time, and then you need to memorize that state.
Right.
Otherwise, it would be impractical if you go over many states and then.
So.
But this,
We can discuss this offline, actually. Yeah, this is a little bit more detailed. Any other questions? Okay, Blake, one more question.
I mean, if you can extend to directory graphs, can you do hypergraphs too?
Sure. Well, we haven't done hyper.
Usually not easy.
So, yeah.
I mean, I'm joking a little bit, but in all seriousness, hypergraphs are a more inclusive model. Have you thought about extension?
We have, and I would say that the description that we have now describes sort of the applications we have in mind, but we're aware of, and I would say that we're mostly application driven, but if there's some cool, if there's a really beautiful, cool theory that could pop out of such an extension, that would be interesting.
Just a comment on that. Any system which is modeled by differential algebraic equations can be cast as hypercubes.
Yes.
So if you have differential equations and algebraic equations, you have the actual nodes as your differential nodes and the algebraic nodes as your hypernodes. So, so the graph actually becomes hypercube.
Yep.
All right. Well, let's thank our speaker.